to go ahead and start off the unit on angular motion. So today we're going to talk about angular kinematics. So again, all year we've been talking about linear motion, so things that go back and forth and side to side and up and down. But now we're going to talk about things that are angular that rotate around. Cool. So first thing we're going to talk about is angular position. So I'm going to go ahead and draw a good old circle. So that's, circles like to rotate. That's what they do. And with this circle, oftentimes the angle that we use to measure like distance for something rotating is going to be theta. So the symbol that we use for angular position is going to be theta. If we want to say the change in angular position, we'll say delta theta. So this is change in angular position. I want you to think about now what type of units we might use for theta. So think about what type of units we might use, write those down, and then check back in on the video. Okay, so let's list out some units. So any type of unit, so it's angular position we're looking at. So again, theta is angular position. So let's see, we could do radians as a typical one that is oftentimes used in math and physics courses. Degrees, that's even more common in our everyday life. Let's see, rotations, things rotate around. Let's see, what else do we got? Revolutions, like the same thing as a rotation. Cool. And we are mostly going to go ahead and use radians. So just a heads up, for most of the work we do this year, we're going to go ahead and do radians. Let's just try one tiny little problem together, and then let's go ahead and go on to angular velocity. So, okay, a second hand of clock moves 30 seconds, so angular displacement of a second hand. So again, try this yourself, and I would recommend drawing a picture and then check back in on the video. Okay, so after you've tried it yourself, I know that the second hand is the one that goes fast, takes 60 seconds to go around. So to go from the start, let's say when it's right at the top at 12, to 30 seconds, that's just going to be halfway around. So that's 180 degrees. Let's see, to go once all the way around, so once around is going to be, I know that from math, is going to be 2 pi radians. So this is just halfway around. So half of 2 pi radians, which is just pi radians. So that is the angular displacement of the second hand of the clock. Sometimes people like to do like ratios to set up things like this. You're welcome to that too. So you might say like, okay, 30 seconds is the time we're dealing with. We're going to try to convert that to an angular quantity. So let's see what things are 1. So to go once all the way around, it's 60 seconds for 2 pi radians. So seconds cancels out, we do some fun old math, and we are just left with pi radians. So that's another way to go about it if you want to do a ratio. And again, that ratio works because seconds cancels out, and we're just left with an angular position quantity. Cool. So let's go ahead and go on to the next. Okay, so now let's go ahead and chat about angular speed and angular velocity. So angular speed, the symbol we're going to use for that is going to be omega. So again, this is omega. In Greek alphabet, it's pronounced omega. And again, this is angular speed or angular velocity. So angular speed slash velocity. And we'll talk about the difference of those two in just a second. So I want you to guess an equation for angular speed and then check back in on the video. Okay, so I know speed is distance over time. So angular speed is going to be angular distance divided by time. So bottom has to be time, or I should say change in time, because it's the time that's changing. Angular distance is just going to be change in theta. Cool. So angular speed is just change in theta over change in time. And if I wanted average angular velocity, I can say delta, or what average W, so it's W with a bar over it, is change in theta over change in time. And I should use that to be more precise. So again, this is average angular velocity. What I want you to think about is what's the difference between a speed and a velocity? Okay, so I know velocity has a speed with a direction. So an angular velocity might just tell us what way something's rotating, whether something is rotating clockwise or counterclockwise. So I oftentimes throw that in when we're dealing with an angular velocity. I'll throw in like, okay, something rotating clockwise or counterclockwise, or in the problem, it might deal with positive or negative quantities, while speed is just the magnitude of something. Cool. And I know I should write down a technical definition too. So again, angular speed or angular velocity is going to be the rate at which angular position changes. Angular position changes. Go ahead and write down some possible units for angular speed or angular velocity, and then I'll write down some. Okay, so oftentimes we'll deal with revolutions per minute. So again, that's revs per minute. We'll do, let's see, what else? Radians per second. We will use radians per second all the time. That'll be our go-to. Maybe we'll use degrees per second, rotations per hour, whatever it is, and on and on and on. Cool. So this is some example units, but you could do any unit of rotation divided by any unit of time, and that's good. Cool. So let's go ahead and go on to solve a couple of problems together. So angular velocity of this, and again, for these problems, try them yourself and then check back in on the video. Okay. So we want the angular velocity of the second hand of a clock in radians per second. Okay. So let's think about a clock. So we have a good old clock. So for the second hand of the clock to go around once, so second hand of the clock, it takes 60 seconds for that big long hand to go around, and it goes through 360 degrees, one rotation, or 2 pi radians, whatever units we need to use. Okay, let's go ahead and write it out. So again, angular velocity is going to be, or I could say average angular velocity is change in theta over change in time. So I need to think of quantities that are like once around. So change in theta is, let's see, 2 pi radians to go once around. Time is going to be 60 seconds to go once around. Cool. I got my thing. I can plug it in and let's see what I get. Cool. And I got 0.1 radians per second when I plugged it all in. Let's go ahead and do another one. So for number 2, angular velocity in radians per second of a wheel turning at 25 RPM. This looks like a fun conversion. Okay, let's do it. So, okay, omega equals what? 25 revs per minute. And again, that's per essentially 1 minute. So, oh, I love conversions. So I want this to radians per second. Okay, so let's think about what things are equivalent. So I'll do the easy one first. 1 minute, I know how to convert that to seconds. 1 minute is 60 seconds. Cool. Minutes and minutes cancels. Okay, so now I have revs I need to convert to radians. So 1 revolution to go once all the way around, I know that is 2 pi radians. So that is going to cancel. I'm left with radians per second. I can now plug it into my good old calc. Cool. And I got 2.62 radians per second. Cool. The next one too, I'll just go through it real quick, but feel free to skip along if you're like, I already feel good on this stuff. So let's see. Record player moves through 675 degrees in 0.3 seconds. So omega is, again, change in theta over change in time. So for every 675 degrees, we got 0.3 seconds. Cool. So let's see. Degrees, seconds is good. We just need to convert degrees to radians. So let's see. There are 360. Oh my goodness, I'm doing silly mistakes. I was going to say 365 degrees. That's days in a year. 360 degrees, excuse me, in 1 revolution. Okay, so now we have revolution. So now I need revolutions to radians. So I know there's 1 revolution or 1 rotation in 2 pi radians. Cancel, and we're left with radians per second. And I got 39 radians per second. Cool. Cool. So the last thing we're going to chat about is angular acceleration. So go ahead and write down a guess for angular acceleration, the definition, and then check back into the video. I also encourage you to write down an equation for average angular acceleration. Okay. So now that you've done that, an angular acceleration is just, regular acceleration is the rate at which velocity changes. So angular acceleration is the rate at which angular velocity changes, So the symbol we're going to use for angular acceleration is going to be the symbol alpha. And again, it's called alpha. My students love to call it fishy. That's what they love to call it. So, but anyways, it is technically alpha. Cool. So let's go ahead and get an equation. So for average angular acceleration, so again, we know the symbol for average is going to be whatever the quantity is with a line over it. So average alpha, we got it, or average fish. Cool. So it's going to be the rate at which angular velocity changes. Oh my goodness, I left something out. Rate at which angular velocity changes. No, that's cool. A rate is the change of velocity per time, so I'm good. Excuse me. So it is going to be the change in angular velocity. So again, angular velocity is omega over change in time. Change in omega, I want you to think about how we might find change of omega. I think of that as that's going to be like omega f minus omega I over change in time. Cool. So let's go ahead and write down some possible units for angular acceleration. It's an acceleration, so it's per time squared. So oftentimes for units, we're going to use like radians per second squared. We might see like revolutions per minute squared. It could be like degrees per hour squared, whatever you want, or like radians. People might write radians per second squared as radians per second. Any of those is totally fine. Cool. Try these two problems below and then check back in on the video. Cool. Let's go ahead and look at it. So we have this good old bike problem. So it starts from an angular velocity of 2 radians per second. I'm going to write down my given. So omega I is 2 radians per second. Has a final angular speed of 5.6. Let's write that down. So omega F is 5.6 radians per second. 7 seconds. Let's think about what that is. Seconds is the time. So that is just going to be the change in time. And we want the average angular acceleration. Cool. Let's go ahead and plug it all into that good old equation we just wrote above. So again, it's omega F minus omega I over change in t. So what? 5.6 minus 2 over 7. Cool. So let's look at the last one. So course of 1 hour, what is the angular acceleration of the minute hand? So I'm going to think of average angular acceleration. So what's happening to that minute hand as it goes around? Overall, that minute hand, it is a pretty steady movement. Let's assume it's like perfectly steady movement. If it is not changing its velocity at all, it's rotating in the same direction at the same rate, then there is no acceleration. So I'm going to say acceleration is approximately 0 radians per second squared. Cool. Again, because if we think of something spinning, to accelerate, it would either need to change direction, so rotate from clockwise to counterclockwise, or vice versa, or it would need to, so again, that would be change direction, or it would need to speed up, or it would need to slow down. So those, again, are all of our options, if I can write the word slow down, for something to accelerate in general. Cool.